Good morning. Hope you enjoyed your break. We have our exam coming up on Wednesday. Tomorrow night there will be a review session at 8:30. And I responded to a request about that on Piazza, and I believe I posted a link there. I will follow up with another email and a link so that you guys know where to go. And as I said, that's a time for you to ask me questions. So I hope you'll come prepared, and I'll walk through answers to questions. I'm happy to spend an hour or two doing that. It's not, I want to take the time to do a good job there. Last time we started talking about delta O in more detail, and how pi acceptors and pi donors will modulate the T2G set in an octahedral case, right? T2G set has pi symmetry. So if you have pi accepting ligands that can take electrons on the metal and stabilize them by being positive, when those ligands are positively charged or partially positively charged, when they're pi acids. Let's see here, I'm going to spotlight myself. When they're positively charged pi acid type ligands, any electrons on the metal center will drop in energy. And when they're donors, it'll push up electrons on the metal. And so the T2G and EG set are the orbitals that are like electrons on the metal. And so we looked at how you can have a series of different molecules from pi acceptors like carbon monoxide and nitrosonium to sigma donor only kinds of ligands like ammonia or water to pi donors, and that will move that spacing around. And this gives rise to different spin states, turns out, different electronic configurations. We'll talk about that a little bit more today. And let's see here. Yeah, we talked about how spin orbit coupling and stronger bonding in the 5D and 4D transition metals tends to give rise to low spin complexes. And so really it's only the 3D transition metals that give you not in all cases, but the majority of cases where you end up with a high electronic spin, you have a 3D transition metal. And typically with a pi donor type of a ligand, or when you have a weak sigma donor, because the sigma star level is that EG level that moves up and down. So weaker sigma donors means smaller spacing, which means more easily promoted. Okay, so that's an important thing to be aware of. So we're going to go through and do a series of structures here to kind of help drill some of those ideas in. Okay. All right, so we're going to do, maybe I'll change my paper type here too. So we're going to look at some transition metals. The delta O, the term symbol, and the splitting pattern. So let's start off with our trusty cobalt-3 hexafluoride trianion. So 6 fluoride minuses around a cobalt-3 plus gives you a 3- complex overall. Cobalt has how many d electrons? Cobalt metal. Anybody? Nobody?
It's D7.
Cobalt starts out D9.
Oh, D9. Yeah.
One row just to the left of nickel, palladium, platinum. Nickel, palladium, platinum have 10 d electrons. Cobalt, rhodium, and iridium are adjacent to nickel, palladium, platinum, so they start out with 9. And we concluded this was a cobalt-3 plus, so this complex has 6 d electrons. And it has an electron configuration T2G4 Eg twice. So it is high spin. Now you should have guessed that because fluoride is a pi donor. It's a weakish sigma donor. You have a 3D transition metal that has weaker bonding than a 5D, and it has lower spin orbit coupling. And a 3- charge means that the ligands are kind of spread out from the metal a little bit to reduce the charge density. So that complex is going to have a small delta O, relatively speaking, 13,000. This is in inverse centimeters. And it has a quintet T ground state that looks like this. There's your T2G4 Eg twice. All right, now let's take a look at cobalt 2. Hexaquo ion. So this is a 2+ complex because you have 6 neutral ligands, 6 water ligands around a cobalt 2+. So that means D7 because cobalt starts out with 9 d electrons. This compound is T2G5 Eg twice, and it is also high spin. The delta O here is 9,000. And it has a quartet T state. I'm always confused by this example. I'm going to come back to that in just a second. Let's do, for comparison, cobalt-3 hexaquo 3+. So now we're going to take one electron out. That's going to make us a D6 ion. And this compound, whoops, is T2G6 Eg0. This molecule is low spin, and it has an 18,000 wave number delta O. And its d orbital splitting looks like this. Can anybody tell me the term symbol? How do we do term symbols? This guy is a quartet because it has 1, 2, 3 unpaired electrons. This guy is a quintet because it has 1, 2, 3, 4 unpaired electrons. This has no unpaired electrons, so therefore it is it's going to be the number of unpaired electrons plus 1.
It's a singlet, right? It's a singlet.
And here, what is the degeneracy of this orbital splitting or this electron configuration? It's 3, because you can move this electron here to this position or to this position. So there's 3 ways to write that, and that makes it a T for triply degenerate. Same thing here, there's 3 positions you could put that hole. So it's also a T. What's the degeneracy of this? There are no other ways to write it, and so it's an A. So this is a singlet A. Okay, now notice what happened. We went from hexaqual ion to hexaqual ion 2+ to 3+. What happens when you increase the charge on the metal? It becomes more acidic. By acidic, I mean the metal becomes more electron withdrawing. And that's going to pull the ligands in more tightly, because those ligands are donating electronic density to the cobalt. So the cobalt says, I'm hungry, I need some more charge, negative charge. And it pulls the electron pairs toward itself and shortens the bond lengths, strengthens the bonding. And when you strengthen the bonding, you're going to increase this spacing here, because this orbital energy is representative of the sigma bond strength. This is non-bonding in this example because water is only a sigma donor. So the only interaction that's relevant is the energy of this sigma star here, okay? And when you pull the ligands in more tightly, you're going to push this up in energy because the bond strengths are going to increase. So when you do that, you end up with a delta O that's 18,000 wave numbers instead of 9,000 wave numbers. And now promoting an electron to go to the high spin state is unfavorable. Okay, now let's look at cobalt-3 hexafluoride. Now we've got a cobalt-3 ion, very acidic like this cobalt-3 ion is, but we've got fluoride donors, a 3- charge, and some pi donating character. And all of those things will reduce that delta O. So if you want to compare this guy and this guy, you might say the delta O went down by 5,000 wave numbers because we've got a 3- charge and pi donor ligands. Pi donor ligands push this up in energy. These electrons have a repulsive interaction with the lone pairs on fluorine of pi symmetry. Those lone pairs push up that level and shrink this delta O spacing. All right, let's do some more. This time we're going to do cobalt-2 hexamine. Amines are neutral, so cobalt-2 is really 2+. And we're back to D7, and we're going to compare this cobalt-2 with a cobalt-3 hexamine. D7 and D6 again. So an amine ligand is a stronger donator than an aquo ligand. So it's going to make the EG level, the sigma star level, go up in energy. And that's going to increase the delta O. So if I had to guess, the delta O is larger than this guy here in this compound, both 3+ ions, but now stronger ligands. So I should get more than 18,000 wave numbers, which means this compound is going to be low spin also. And I'm correct, according to my notes. 23,000 wave numbers. It's also going to be a singlet A. Now, this one's a little bit trickier. It turns out that cobalt-2 hexamine is high spin. And 12,000 wave numbers, delta O. Similar to that fluoride complex up there. So we're back in quartet A land. Sorry, quartet T. Okay. So you can see for the cobalt-2 ions, you've got 9,000 and 12,000. So you get a 3,000 wave number difference on going from aqua ligands to ammonia ligands. And in the cobalt-3 case, you go from 18 to 23. So 5,000 wave number difference. So the strength of the donor ligand and its impact on delta O is actually sensitive to the charge. More important to have stronger donor ligands when the metal ion is 3+ instead of 2+.
I think there's an electron missing in that last one.
You are right. Thank you. Is that Sherelle?
Yes, hi.
Hi. All right. Yeah, and over Zoom, you get to know people's voices as opposed to their faces. All right, so let's do another one here. We're going to take a look at cobalt-3 hexacyanide. We're back in 3- territory. D6. Anybody want to guess? High spin or low spin? Anybody? What kind of a ligand is a cyanide?
Sigma donor.
Cyanide is a very good sigma donor. Carbon anions, pretty good sigma donor. Does it have any pi characteristics?
Well, aren't all of its pi electrons used up? So no, I would say.
Well, cyanide is a pi acceptor, kind of
Right.
like carbon monoxide is. And it's a weaker pi acceptor. Cyanide is both a good sigma donor and a pi acceptor. And so cyanide is a classic example of a strong field ligand because the sigma donating power raises the EG and the pi accepting power lowers the T2G. Okay, so does that mean we're going to be in high spin territory or low spin territory?
High spin.
All right, let's have a show of hands, please. Would you indicate on the part on your Zoom screen how many of you like high spin? Okay, we have a minority of people who like high spin. Obviously, it's hard to know the answer to this because you don't, it's 3-. But cyanide is a much stronger donor than the other anions on this list, and it has this pi accepting character. And so both of those things are going to increase the spacing of the delta O. On the list of ligands that are that rank order their field, strong field versus low field character, cyanide is pretty far to the left. So out of everything on here so far, this thing is most likely to be low spin. And the delta O is 32,000.
So this would be that like the delta O is greater than like the pairing energy, right? That's kind of how you can like mathematically tell.
That's right, yeah. When you promote electrons across the gap, you have to pay the energy of promotion, but you get exchange out and you reduce Coulombic forces. So that's how you tell exactly. So strong field ligands are those that increase that spacing, and they make you pay a higher penalty to promote an electron to go to high spin. Okay, so cyanide, good sigma donor, raises that EG level, pi acceptor lowers it. All right, let's go take a look at a new compound here. We're going to go to iron. Now we're iron 2, hexaquil. This guy is 2+. Iron, ruthenium, and osmium are one step to the left of cobalt, rhodium, iridium. It's helpful to know that one. Iron is D8. So when we're in iron 2, we have 60 electrons remaining. And this compound, T2G4, EG twice, is high spin. Now you could have guessed that because you get more electrons in the high spin state. You get more exchange energy, and so these weak field water ligands on a metal center that has a lot of unpaired spins. Now we're talking about how many are we going to have? We're going to have 4 electrons that are unpaired. So that's a lot of exchange interactions, and that means that the cost of promoting the electron isn't so bad because you end up with this quintet T state. Forgot my singlet A up here. Let's take a look at D5 manganese, 1,2 hexaquil ion. T2G, EG. Is this one going to be high spin or low spin? D5, 3D transition metal, weak field ligands, definitely high spin. You get 5 unpaired spins. That's a lot of exchange. Most of the time, manganese is going to go for high spin. This thing term symbol. How many unpaired electrons? 5 unpaired electrons. That means it's going to be a sextet. Is there any degeneracy? Can you rearrange these things in a way that, you know, there's no electrons to move around or holes to move around. So this thing is a sextet A. Let's take a look at D5 iron 3. Whoa, baby. Hexaquil ion. Now we've got a 3+ iron. High spin or low spin? This is on the border. It's high spin. Why does it turn out high spin? We already did cobalt hexaquo 3+ ion. There you get to a low spin situation. Here, the spacing is 14,000 wave numbers. It's high spin because there's 5 electrons. Lots of exchange to be had there. Okay, D5 is kind of special. Lots of exchange energy to be had in the high spin state. Okay. All right, so you got to get good at doing that. The relevant point here is how strong is the bonding between the ligands and the metal. When the metal is 3+ or highly positively charged, the bonding gets stronger. When the ligands are strong donors, the bonding gets stronger. When the ligands are strong donors and pi acceptors, and there are electrons on the metal center, the bonding gets stronger. So weak donors and pi donors, that spacing is small. And so you're going to have to use your intuition about that to guess as to whether something's going to be high spin or low spin. All right, so let's see here. I'm going to ditch let's talk spectroscopy. So we're talking optical spectroscopy now. And there are a couple of types of transitions that are of interest. Okay, all of these metal ions are beautifully colored. And one of the ways you can get color are from ligand field transitions, otherwise known as D to D transitions. Another type of transition is a charge transfer. And there are 2 types that people tend to be interested in. One is where the metal sends electrons over to the ligand. MLCT is what people call that, metal to ligand charge transfer. There's also a version where the ligand sends charge to the metal. That's called an LMCT, ligand to metal charge transfer. D to D transitions are kind of weak. They give pale colors. Charge transfer transitions are strong. They give deep colors. So we're going to talk about selection rules. This just means how probable is the transition. So, an important consideration in a D to D transition. Transitions between different spin multiplicities are not allowed. This is a relatively strict rule, but it's getting hard to read my writing with this pen. I've got to switch. Phosphorescence. Phosphorescence is an example of a luminescence transition involving different spin multiplicities. So phosphorescence happens, but it's not that probable. It tends to be slow. Glow-in-the-dark materials are phosphorescent. Yeah, one more note about that. This spin selectivity thing really doesn't work very well for 4D and 5D metals. And the reason is that there are not well-defined spin states. There are spin orbit states. Spin orbit coupling is large. And so you can't say this is a singlet and that's a triplet, because the spin state and the orbital angular momentum are kind of mixed. So you have to talk about spin orbit states. And that means that optical transitions between those spin orbit levels are more allowed, and the spin multiplicity stuff doesn't really mean as much. Especially for lanthanides. So lanthanides are really brightly luminescent, involving F to F transitions. F to F orbital transitions. You have strong spin orbit coupling. And so, in fact, most of the luminescent materials used in solid state lighting are F orbital elements. Many of them, anyway. Cerium, terbium, europium, dysprosium. Those compounds are wonderfully luminescent. Okay, let's see here. So, I forgot to mention phosphorescence has a photoluminescence lifetime of about 10 to the -3 to 10 to the 0 seconds. So the half-life for the luminescence might be 1 second in length. You could see it decay by eye. All right, so rule number 2 is called the Laporte selection rule. And allowed transitions are G to U or U to G. What is G and U? Garada and Ungarada. Tells you about whether or not there's an inversion center, right? This only applies if you have inversion symmetry. So in TD, there's no inversion symmetry, no Laporte rule. In octahedral, you have to pay attention to that. Now, D to D transitions are they ever G to U or U to G? There's no inversion symmetry. Okay, so D to D transitions are forbidden according to the Laporte selection rule. However, vibrations help these transitions to happen. Okay. So D to D, S to D, D to S, P to P, and F to F, all disallowed by Laporte. P to D, S to P, those are allowed. Okay, so these D to D transitions have epsilons of 0.1 to 100 per molar per centimeter. Okay, an epsilon tells you about the strength of the absorption or the probability of the absorption. These are low numbers. D to D transitions are forbidden by Laporte, and so they're not very strong. If the transition metal complex is itself has an inversion center, these issues are more important. If it's tetrahedral and there's no inversion symmetry, it's less important. So tetrahedral compounds are more likely to show you a D to D transition. Octahedral compounds are less likely to show you a D to D transition. So if you measure the strength of the absorption, or you want to know whether your molecule is going to be luminescent, the probability of that transition is related to the symmetry. And an octahedral compound will have an epsilon closer to 0.1, and a tetrahedral compound will have an epsilon closer to 100. Let's talk charge transfer. LMCT and MLCT are intense. When the electron gets pushed from the ligand to the metal, or from the metal to the ligand, there's an electrical motion that couples to the electric field of a photon. So charge transfer is something that can couple to an electric field moment of a photon, and it makes those transitions probable. They are said to be called electric dipole allowed. There's a dipole that builds up as the charge is transferred. And this couples to the exciting photons electric field. can actually just take a pair of capacitors, like parallel plate, and drive a frequency across that parallel plate, and that electric motion across the parallel plates can excite a transition if the frequency is right. Okay, so the photon brings in an oscillating field, and it helps to push charges around. These things tend to have epsilons of 10 to the 3 or 10 to the 5 per molar per centimeter. So we're talking about orders of magnitude more intense. Let's talk about LMCT for a minute. So you start out with some metal ligand complex, you add a photon, and then the product looks like this, where you've transferred an electron from a ligand to the metal, and the ligand gets oxidized and the metal gets reduced. So if this process is easy, the photon energy required to make it happen is small. So metals that are oxidizing are more easily reduced. And the photon energy required is smaller. So metals like iron 3, cobalt 3, manganese 7, chromium 6, all oxidizing. Low energy LMCT. Similarly, ligands that are good reducing agents help this process to happen with low energy. So O2 minus, X minus, N3 azid anion, thiocyanate. These are all reducing. You end up with low energy LMCT. So for example, permanganate. Sorry. Permanganate is purple in color, deep purple color. And the energy of the LMCT transitions are about 19,000. Chromium 6. This is yellow-orange. Its MLCT is 26,000 wave numbers. Vanadium, the vanadate ion. This guy is pale yellow. And the energy of the LMCT is 36,000. So as you go from manganese toward vanadium, you're going from a +7 metal center to a +5 metal center. And the +7 metal center is going to be more oxidizing. You're also going from right to left in the periodic table. And so, you know, the elements toward the right are more electronegative. So you have a more electronegative manganese ion with a higher charge state. And so that's a metal that's going to be more easily reduced. And you can see that in the energy of the LMCT transition. It only takes 19,000 wave numbers to excite an electron from an oxide ligand anion to a manganese center, versus 36 for vanadium. Okay. Now, the color that's listed there is the color of the solution of the ion that you see. And that's a little bit counterintuitive because purple or blue is a high energy color. Yellow is a low energy color. But it looks this way because the color of the solution is the color that's not absorbed. Right? What you see is what's left over. So if something comes out purple, it means that you're absorbing the high energy parts of the spectrum. Sorry, it means that you're absorbing the low energy parts of the spectrum and not the high energy parts, okay? Remember the color wheel. Red, orange, yellow, green, blue, purple. So white light minus yellow light equals what color? You can just look here. These two guys are across from each other. So if you subtract yellow light, you're going to be left with purple. So purple compounds absorb yellow, which is a low energy, or red, which is a low energy photon. Let's go back and take a look at a few others. How about MnO4 minus versus technetium O4 minus versus rhenium O4 minus. So the energy of the LMCT state that we're talking about here, how is it going to change when you go from manganese to rhenium? You need to know is whether or not rhenium or manganese is more easily reduced. Manganese is the most powerful oxidant in that set, rhenium the least. The bonding is stronger between the metal and the ligands, and the metal is more electropositive as you go down. And so it takes less energy to promote that electron from the oxygen and put it onto the manganese. So the energy of the LMCT state goes up as you go from manganese to rhenium. How about chromium? Tungsten and molybdenum. Where are those in the periodic table? Yi Chung points out, same trend. Chromium, molybdenum, tungsten are on top of one another. Those of you interested in bikes or history might know the name chromoly steel. Chromoly is another name for chrome. Chromoly is a mixture of chromium and molybdenum, and it's used to make steel. So that helps you know that chromium and molybdenum go together. They happen in the same column of the periodic table. You got to remember tungsten though. All right, so same trend here. The energy of the LMCT goes up. All right. Similar trend with ligands. Take a look at osmium, hexaiodide. Now we're doing osmium 3. So that makes this a 3- compound. No, we're not doing that, sorry. We're doing osmium 4. You have 6 iodide anions around one transition metal that we're saying is 4+, so the whole thing should be 2-. Let's compare that with the hexabromide. And the chloride. Who's more easily reduced or oxidized? Which photon energy is going to be the smallest? Iodide is more easily oxidized than chloride because iodide is bigger. And so pulling the electron off of iodide takes less energy. So this band is about 11,500 to about 18,000 wave numbers. Here we go from 17,000 to 25,000. And then 24,000 to 30,000. So you'd be amazed at how useful this kind of thinking is. You look at your reaction, you throw in a ligand, it changes colors. It turns blue or it turns yellow. And on the basis of that, you can say, oh, I think it happened because I put in a pi acceptor. And the pi acceptor is increasing the, the charge transfer energy. Or why did my thing turn green? Well, you can think about the energies of these transitions and what you've done and try and make a correlation there. Metal to ligand charge transfer becomes visible when the ligand is easily reduced. De-roost. Okay, so things like carbon monoxide Aromatic systems, NO+. Things that have pi systems that are electron withdrawing or delocalized, like aromatic ligands, they tend to have lower energy MLCTs. Chromium hexacarbonyl is D6. The E of the ligand to metal charge transfer, sorry. Energy of the metal to ligand charge transfer band here is 35,000, which is just outside of the visible. You go over to manganese, the D6 ion is positively charged. Harder to oxidize the metal, so the energy of the transition goes up. Let's take a look at some chemical manifestations. Of delta O. One of them is ligand substitution. So for example, imagine you have an iron 2 hexagual ion. And we're going to use a O16 labeled water, and we're going to put it into O18 water. We're going to watch it exchange. So we're replacing an O16 with an O18. It turns out the way that this happens is by dissociation. So you end up with a 5-coordinate compound. And that 5-coordinate compound could go and pick up the O16 water again, or I can pick up the O18 water, and so on and so forth. Okay, so it goes by dissociation, and that's the slow step. So the overall rate of this interconversion is dictated by the kinetics of losing a water ligand and going from 6-coordinate to 5-coordinate. The kinetics are controlled by bond strength. Not always true. Kinetics are not always controlled by the bond strength here. But in this case, they are, because the mechanism involves breaking a bond. You got to pay that penalty, okay? So what that means is that you end up with, you end up being able to predict the exchange rate constant the K1, the loss of water. And it depends upon the identity of the starting metal complex. So say you have iron 2, D6, this guy is high spin. Okay. And it has a 10 to the 6th per second exchange rate constant, 1,000,000 times per second. That's really fast. And the reason is that it's high spin. And there's an electron in the antibonding, metal ligand antibonding orbital. That's the EG level. With an electron in that orbital, that's right in the way of this water molecule, and it makes it favorable for the water molecule to dissociate. When you put an electron into an antibonding level, it makes the bond want to break. So let's do the D5 case. This guy is also high spin, but now it's 3 plus. 3 plus metal ion is more acidic. You have a, it's slower. Because of that 3 plus ion, but it's still high spin. You still have an electron up in that orbital. Let's do D7 cobalt. D7 cobalt, still high spin. We're back up to 10 to the 6 because it's a 2 plus ion. The 3 plus ion, however, is a low spin. The 3 plus ion is low spin, and its exchange rate constant is 10 to the minus 2. Okay, so low spin means no more electrons in the sigma star orbital, right? No more antibonding orbital populated any longer. And so now it's not that favorable, and the water molecule will stick better to the metal center because there's no electron in its way. Let's take a look at another cobalt 3 ion. This time we're going to put in some ammonia ligands, 5 of them. So we're still cobalt 3 plus, but now we have ammonias instead of waters. What is that going to do? How is ammonia different than water?
It's a stronger donor.
Ammonia is a stronger donor. It's a base. If you dissolve ammonia in water, you get a basic solution. Good for cleaning stuff, like windows. And it's a stronger donor that will neutralize the charge. So you have a low spin, 3 plus ion. And it turns out that it's actually even slower. Which is something that is not very well understood by me. What I have in my notes here is that water has a weaker metal ligand bond than ammonia, but the delta O is larger. Than in cobalt-3. Three plus ion. Now, I'm going to tell you, I don't think that this is well understood. Okay, and it's because it turns out this number is not very well understood. This is actually much faster than it should be. There's a long debate about why. People think, in fact, that there's a little bit of cobalt-2 in this solution. It's not actually cobalt-3 only. So you go measure an exchange rate constant of 10 to the minus 2, but it's actually quite a bit slower than that. So the difference between these two may not reflect reality. Let's take a look at a more clear-cut case. Let's look at the cobalt hexamine 3+ is also low spin. Its ammonia substitution kinetics are 10 to the minus 10. So ammonia is more strongly bound than water. And at this rate of exchange, it takes about 200 years for this process to go 50% of the way. The half-life for dissociation of ammonia from cobalt hexamine 3+ ion is 200 years. That's a pretty stable compound. Okay, so a couple cool things there, right? You got an 8 order of magnitude difference on changing spin state. The 2 to 3 conversion, low spin to high spin, or I guess high spin to low spin, causes an 8 order of magnitude change, a factor of 100 million. So the rate of ligand substitution is really sensitive to the population of that sigma star antibonding level. So let's take a look at metal ligand distances for a second. Metal ligand distances are sensitive to delta O. And the spin state. You can imagine that when you have a high spin case and you have electrons in the antibonding level, you weaken those bonds and they become longer. So we're going to take a look at the energy versus the cobalt oxygen distance here. And we're going to compare two cases. we're going to look at T2G 4 EG twice. So this is 6 electrons for cobalt. This would be the cobalt 3 hexaquo ion. And we're also going to look at T2G 6 EG0. So this is the A1 state and the quintet T state. And what you'll notice here is that these guys, sorry, this is the distance for the cold oxygen bond. They're different by 0.15 angstroms. That's a big change. 0.15 angstroms is a lot. So the low spin complex has the shorter bond distance. And generally speaking, the shorter the distance, the greater the splitting. There's another one that we have to talk about. We actually end up with distortions from octahedral. Classic example of this is chromium 2 hexaquo ion. This thing is D4. And it turns out that this molecule looks something like this, where the axial distance is about 2.4 angstroms. The equatorial distance is 2.1 angstroms. Actually, 2.0, sorry. Okay, so these this compound has 2 different bond lengths. This is an example of what's called a Jahn-Teller distortion. What is that? Jahn-Teller distortion Jahn-Teller distortion results when a molecule can actually save energy by distorting. And it arises when you have an electronic degeneracy. Okay, and the molecule will distort to eliminate that degeneracy. So let's take a look here for a second at this chromium 2 hexaquo ion 2 plus D4. in octahedral symmetry, it has an EG, which is dz squared, dx squared minus y squared, T2G, xy, xz, yz, right? And this thing here is sigma star, and this is non-bonding. And you have this degeneracy problem where you have two states here with one electron. I'm almost done. It undergoes Jahn-Teller distortion, and it does this. It splits that degeneracy. It strengthens the bonding to dx squared minus y squared, and it weakens the bonding to dz squared. So this guy is octahedral and has a quintet E state. Get 4 unpaired electrons, that makes it a quintet. You have one degeneracy, the doubly degenerate situation. That's an E set, or that's an E multiplicity. So quintet E, and it turns into a compound that's D4H in symmetry. It still has 5 unpaired electrons, but now there's no more degeneracy. So that's a quintet A. So the distortion, the stretching along that bond does that. It changes the energy of the z squared and the x squared minus y squared levels, and it eliminates that degeneracy. And in so doing, it weakens it lowers the energy of that anti-bonding electron, and it strengthens the bonding interaction with the water ligands in the equatorial plane. So the molecule moves itself around, rejiggers its situation to capitalize on its electronic structure, and it eliminates the degeneracy in doing so. Okay, so I'm gonna stop there. We'll revisit this last time because I know that was a little bit quick. And I will hang out for a few minutes and take questions. I unfortunately I'm giving a lecture at the Washington State University today, so I only have a few minutes after class to chat, but I'm happy to talk. And otherwise, I will see you tomorrow night. I will follow up with an email and a link, or you can go look at the one I posted on Piazza, and I'll look forward to seeing you then.
Hi, Professor Owen. I just had a quick question.
Sure.